In the vast dark, a star 2,000 times bigger than our Sun may be dying right now. Its surface could reach past the orbit of Saturn. Its light takes 19,000 years to reach us. So, when we look at it tonight, we are not looking at now. We are looking at the past, and what we see may already be gone. We call it Stephenson 218, a star so massive that our entire Sun would look like a grain of dust beside it. A star cooler than a candle flame compared to most stars, yet more than 400,000 times brighter than our Sun. Tonight, we travel there. We will watch it swell, shudder, and shed pieces of itself into space. We will meet the star that stole its crown and the astronomer who found it by accident. We will ask what happens in the final years before a giant like this tears itself apart. If this kind of story pulls you in, stick around and subscribe. More is coming. Prepare yourselves. We begin. Picture two objects. One weighs as much as a truck. The other is the size of a house, but light as a balloon. Which one is bigger? That question sits at the heart of every biggest star claim you have ever heard. When astronomers say a star is the largest known, they almost never mean the heaviest. They mean the widest, the one that would take up the most room if you could stand next to it. This matters because size and weight do not always travel together. A star can weigh 60 times more than our Sun and still be smaller than one that weighs only 20 times more. It sounds backward, but stars are not solid balls of rock. They are made of gas, held together by their own gravity and pushed outward by the heat of their core. Change that balance, and the same amount of matter can puff up like a marshmallow over a fire, or shrink down into something dense and tight. So when we talk about the largest star in the universe, we are talking about radius, the distance from the center of the star to its outer edge, not its mass, not its brightness, just how far its surface reaches into space. That distinction becomes strange fast. Some of the widest stars ever measured are not even that heavy compared to other giants. They have simply entered a stage of life where their outer layers have swelled out to enormous distances, thin and stretched, like the skin of a balloon blown up almost to bursting. And measuring that almost to bursting point is far harder than it sounds. You cannot walk up to a star with a tape measure. Every size we know comes from indirect clues. Astronomers measure how bright a star appears, figure out how far away it is, and then work backward to guess its true size. Every step in that chain carries uncertainty. Get the distance wrong by a little, and the size estimate can be wrong by a lot. This is why the title of largest known star has changed hands again and again over the last century. Not because stars are shrinking or growing on human timescales. They are not. The title changes because our tools improve, our distance measurements sharpen, and old estimates get corrected. Tonight, one name currently holds that title, at least for now. A red star buried nearly 19,000 light-years from Earth, so wide that if you dropped it into the center of our solar system, its surface could reach past the orbit of Saturn. Its name is Stephenson 218, and it may be dying. Before we can understand what dying means for something this massive, we need to understand what we are actually looking at, because everything about this star breaks the picture you probably have in your head of what a star should look like. You picture the Sunday blazing white-yellow, painfully bright, radiating heat you can feel from 93 million miles away. Now forget that picture completely. The star we are about to meet does not look like that at all. It glows a deep, smoldering red. It is, in a strange twist, one of the coolest stars ever measured, even while being one of the most enormous objects in our galaxy. Big does not mean hot, big does not mean young, and in this case, big might mean the final act of a stellar life that started millions of years ago in a crowded cluster of stars that almost went unnoticed by science entirely. That story starts in 1990, with an astronomer squinting at infrared data, about to stumble onto one of the strangest discoveries in modern astronomy. Somewhere in the constellation Scutum, a patch of sky so faint it holds no star bright enough to see with your bare eyes, sits an object that could swallow the orbit of Saturn. Its name is Stephenson 2-18. Astronomers also call it Saint 2-18, or by the stranger label, Stephenson 2 DFK1. None of those names sound impressive, but the numbers behind them are almost impossible to picture. Current estimates put its radius at around 2,150 times the radius of our Sunday. Try to hold that number in your head for a second. Our Sun already holds 99% of all the mass in our entire solar system. It swallows more than 1 million Earths, and Stephenson 2-18 could be over 2,000 times wider than that. If you swapped it in for our Sun right now, its surface would not stop at Earth. It would not stop at Mars or Jupiter. It could stretch out past Saturn, one of the outer giants of our solar system, nearly 900 million miles from where our Sun currently sits. Its volume, if the numbers hold, would be close to 10 billion times the volume of our Sunday. 10 billion suns could fit inside the space this one star occupies. And yet, despite being almost unimaginably large, Stephenson 2-18 is not the heaviest star we know. Size and weight are different measurements, and this star proves exactly why that distinction matters. It is bright, wide, and swollen, but its mass remains one of the most uncertain numbers scientists have yet to pin down. What we do know is its brightness. Stephenson 2-18 shines with roughly 440,000 times the light output of our Sunday. That number alone would place it among the most luminous stars in our galaxy, even without factoring in its jaw-dropping size. Here is where things get strange. You would expect an object shining that bright to also be blisteringly hot. Instead, its surface temperature sits at around 3,200 degrees on the Kelvin scale, which converts to roughly 5,300 degrees Fahrenheit. That sounds hot by human standards, hot enough to melt steel in seconds. But compared to our Sun's surface, which burns at almost 10,000 degrees Fahrenheit, Stephenson 2-18 runs remarkably cool. That cool temperature is exactly why the star glows deep red instead of white or blue. In the world of stars, red does not mean gentle. It means enormous, aging, and unstable. Astronomers classify Stephenson 2-18 as a red supergiant, possibly even further along the extreme end of that category, called a red hypergiant. Both classifications describe massive stars nearing the end of their lives, stars that have swollen to catastrophic size as their internal furnace begins struggling to hold itself together. But before we go deeper into what that struggle actually looks like, there is something you need to understand about how we know any of this at all. Nobody has flown a spacecraft to Stephenson 2-18. Nobody has taken a close-up photo of its surface. Every fact you just heard came from light, faint, ancient light that left this star thousands of years ago and is only now reaching telescopes on Earth. Which raises an uncomfortable question: how much of what we think we know might already be wrong? Stand outside on a clear night and try to guess how far away a distant streetlight is, using nothing but how bright it looks. A close, dim bulb and a distant, powerful one can appear exactly the same to your eyes. Without more information, you would be guessing blind. That is essentially the problem astronomers face with Stephenson 2-18, except the streetlight sits 19,000 light-years away, buried behind thick clouds of galactic dust. To pin down a star's size, scientists need 3 pieces of information working together. How bright the star actually is, not just how bright it looks, how far away it sits, and how hot its surface burns. Get any one of those 3 wrong, and the size estimate collapses like a house built on sand. Distance is the hardest part by far. Stephenson 2-18 sits deep in the plane of our galaxy, in a direction packed with gas and dust that blocks and scatters starlight before it ever reaches us. Astronomers have to correct for that interference, then rely on techniques like measuring how fast the region is moving relative to Earth to estimate distance. It is a bit like judging how far away a truck is by listening to the pitch of its engine as it passes. Useful, but far from perfect. When Stephenson 2-18 was first noticed in 1990, the distance estimate placed it almost 100,000 light-years away. near the very edge of our galaxy. Later studies, using better techniques, brought that number down dramatically to somewhere closer to 19,000 light-years. That is a massive correction, and every time the distance estimate shifted, the size estimate shifted with it. This is the trap hiding inside almost every biggest star headline you will ever read. A closer star appears fainter than a distant one, giving off the same amount of light. If astronomers slightly misjudge the distance, they misjudge the star's true brightness, and that error carries straight through to their estimate of its size. We saw this exact story play out with a different star entirely, one that used to hold the largest known title before Stephenson 2-18 took it. Its estimated size dropped by more than half once astronomers recalculated its true distance using more precise data. The star did not shrink. Our understanding of the star grew more accurate. That is the uncomfortable truth sitting underneath every number in this story. Stephenson 2-18's radius of 2,150 solar radii comes with real uncertainty attached. Some scientists consider it possibly overestimated. A few even question whether the star fully belongs to the cluster it is named after, or whether it happens to sit in the same direction from Earth purely by coincidence, at a completely different distance. None of that means the number is fantasy. It means science is still working the problem, refining the picture piece by piece, the same way it always has. So why trust any of it? Because even with the uncertainty, multiple independent studies keep landing in the same general range. Different teams, different telescopes, different years, and the star keeps coming back as enormous, luminous, and strange. When separate approaches keep confirming the same rough answer, confidence grows, even while the exact digits stay blurry. Now picture holding that blurry, uncertain, world-breaking number next to something familiar, something you already understand the size of. That comparison is where this story stops being abstract and starts becoming impossible to unsee. Here is an experiment you can run in your head right now. Picture a basketball. Now picture a single grain of sand resting beside it. That comparison, basketball to grain of sand, is roughly the size difference between Stephenson 2-18 and our own Sunday. And our sun is not small. Our sun already holds more than 1 million Earths inside its volume. Earth, next to the sun, looks like a marble sitting beside a beach ball. Now take that beach ball, the sun, and place it next to Stephenson 2-18. The beach ball becomes the marble. The comparison resets itself, over and over, at scales that stop feeling real. Numbers alone cannot fix this problem. Your brain simply was not built to hold quantities like 2,150 solar radii in any meaningful way. So let's try a different approach. Let's walk through it, layer by layer. Start with Earth. Our home planet is roughly 8,000 miles wide, big enough that flying across it takes an entire day. Now, scale up to the Sunday. The sun's diameter stretches to about 865,000 miles. If Earth were the size of a grape, the sun would be about as wide as a large exercise ball. Now, Stephenson 2-18, multiply the sun's radius by roughly 2,150. The result is a star with a radius exceeding 1.4 billion miles. Its full diameter would stretch nearly 3 billion miles across. 3 billion miles is not a number you can picture directly, so picture the trip instead. Light itself, the fastest thing in existence, takes about 8 minutes to travel from the sun to Earth. Crossing the full diameter of Stephenson 2-18 at the speed of light would take over 4 hours. 4 hours of travel at the fastest possible speed in the universe, just to cross from one side of this single object to the other. Here is another way to feel that scale. Commercial jets cruise at around 550 miles an hour, flying non-stop without ever landing to refuel. Crossing the diameter of Stephenson 2-18 would take longer than 600 years. Even our own solar system starts to feel small next to this. The distance from the Sun to Saturn, one of the outer planets, spans roughly 886 million miles. Stephenson 2 to 18's radius alone, just the distance from its center to its surface, already exceeds that entire span. This is not a star that would sit inside our solar system. This is a star that would replace our solar system, swallowing everything out to Saturn's orbit in a single gulp. Mercury, Venus, Earth, Mars, the asteroid belt, Jupiter, all of it, gone, absorbed inside the boiling outer layers of one single star. Sit with that comparison for a moment, because it is not exaggeration. It is closer to the actual physics if this star existed in our neighborhood. Every planet you have ever seen a picture of, everywhere humanity has ever sent a spacecraft short of the outer solar system, would exist inside the body of this one star. And this star is not solid rock the way Earth is. It is a churning, boiling ocean of gas, so thin at its outer edges that its density there is close to nothing at all, more like the inside of a light bulb than a planet's surface. A star this bloated is fragile in ways that seem impossible for something so enormous, which raises the real question waiting at the center of this entire story. If you placed something this massive at the heart of our solar system, what would actually happen to us? Let's run the thought experiment properly. Not just the numbers, but the consequences. Imagine waking up tomorrow, and overnight, some impossible force has swapped our sun for Stephenson 2 to 18. What happens next? In order. The immediate answer is annihilation. But the exact order of destruction is worth walking through, because it reveals just how absurd this star's scale really is. Mercury, the closest planet to our Sun, orbits at about 36 million miles out. Stephenson 2 to 18's surface alone reaches over 1.4 billion miles from its center. Mercury would not orbit this star. Mercury would exist somewhere deep inside it, vaporized instantly, its rock and metal core boiled away into gas within the outer atmosphere of the star itself. Venus, Earth, and Mars follow the same fate. Earth orbits the Sun at about 93 million miles. That distance would place our entire planet roughly 1/15 of the way to this star's actual surface. We would not be looking up at a bright sky. We would be somewhere inside the boiling outer atmosphere of a dying star, gone before we ever understood what happened. Even the asteroid belt, sitting between Mars and Jupiter at roughly 200 to 300 million miles out, would be consumed. Jupiter, the largest planet in our solar system, orbiting at about 484 million miles, would still fall well within this star's outer layers. Only once you reach Saturn, nearly 900 million miles from the center, does the star's surface finally end, according to the higher-end size estimates. Saturn's rings, one of the most photographed sites in our solar system, would sit right at the star's outer boundary, possibly grazing its atmosphere. Everything closer than that would already be gone. This thought experiment matters for a reason beyond shock value. It reframes what big actually means when talking about stars. We often hear size comparisons that feel abstract, numbers stacked on numbers. But swapping Stephenson 2 to 18 into our own solar system turns an abstract measurement into something almost physically felt. Every planet you learned about as a kid, absorbed into a single object. There is something else worth noticing here too. A star this size is not dense. Despite holding a volume close to 10 billion times that of our Sun, its total mass remains far more modest and uncertain, likely somewhere in the range of 10 to 40 times the mass of our Sun, though estimates vary. That means the outer layers of this star are almost shockingly thin, closer to a puffed-out cloud of gas than a solid, tightly packed object. Picture cotton candy instead of a bowling ball. Enormous on the outside, but almost weightless by comparison to its size. This thinness matters, because it hints at instability. A star stretched out this far, held together loosely by gravity that has to fight against the star's own internal pressure, is a star under strain. Not calm, not stable, straining the way an overinflated balloon strains against its own rubber walls. And straining objects eventually tend to do one of two things. They settle or they break. Before we get to which fate awaits Stephenson 2-18, we need to understand something even stranger about this star. Despite being one of the most luminous objects known in our galaxy, it is also, somehow, one of the coolest stars ever measured on its surface. That contradiction, blinding brightness paired with startling coolness, is the next piece of this puzzle. Close your eyes and picture a star. Chances are you picture white light, maybe a hint of yellow, blazing and sharp, the way our own sun looks through a filtered lens. Now delete that image completely, because Stephenson 2-18 looks nothing like that at all. This star glows a deep, smouldering red, not the cheerful red of a stop sign, closer to the color of a dying ember in a fireplace, or the deepest part of a sunset just before the light disappears completely. Color, in the world of stars, is not decoration. It is a direct readout of temperature. Blue and white stars burn ferociously hot, often tens of thousands of degrees at their surface. Yellow stars, like our sun, run cooler, around 10,000 degrees Fahrenheit. Red stars sit at the cool end of that entire scale. Stephenson 2-18 measures at roughly 3,200 degrees on the Kelvin scale, close to 5,300 degrees Fahrenheit, hot enough to instantly vaporize almost anything you know. But compared to other stars, shockingly mild. Astronomers classify this using something called spectral type, essentially a star's fingerprint written in color and temperature. Stephenson 2-18 carries a spectral classification of M6, placing it among the coolest, reddest stars ever confirmed at this scale of size and brightness. Scientists have found this temperature by studying a specific chemical signature in the star's light, a marker tied to titanium oxide, a compound that only shows up clearly in the spectrum of genuinely cool stars. Here lies the contradiction that makes this star so scientifically fascinating. Cool stars are not supposed to be this luminous. Under standard models of how stars evolve, there is a rough ceiling on how bright a star this cool should be able to shine, a boundary sometimes called the Hayashi limit. Stephenson 2-18 appears to sit right at the edge of that boundary, possibly beyond it. That is not a minor detail. That is a star potentially breaking a rule astrophysicists have relied on for decades to describe how stars are supposed to behave. So why is a star this enormous also this cool? The answer connects directly back to its swollen size. Think about a metal rod heated at one end. Stretch that same rod out longer and thinner, using the same amount of heat, and the far end cools down noticeably. Stephenson 2-18 works on a similar principle, though far more extreme. Its outer surface sits so far from its core, spread across such an enormous area, that the heat generated inside gets spread thin by the time it reaches the visible surface. The star is not weak. It is not running low on energy. Its total light output remains staggering, hundreds of thousands of times brighter than our Sunday. That energy is simply distributed across a surface so vast that each patch of it burns comparatively cool. Picture a giant bonfire spread across a football field versus that same amount of wood burning in a small fire pit. Same total heat released, wildly different surface temperature. This detail, a star simultaneously blinding and cool, hints at something deeper happening inside Stephenson 2-18. A star does not simply arrive at this configuration by accident. It gets pushed here through violent internal changes as it runs out of the fuel that kept it stable for millions of years. To understand why, we need to leave the surface of this star behind entirely and travel back to where this whole transformation actually began. Not at the star's edge, but buried deep inside its core, in a nearby cluster that almost slipped past astronomers unnoticed. Here is a pattern that surprises almost everyone the first time they learn it. Across the largest stars ever discovered, a strange rule keeps repeating. The biggest ones tend to be red, not blue, not white. Red? This is not a coincidence tied to Stephenson 2-18 alone. Betelgeuse, one of the most famous red supergiants, visible with the naked eye in the constellation Orion, follows the same pattern. So does VY Canis Majoris, another legendary giant. So does UY Scuti, a star we will meet properly soon. Nearly every record-breaking largest star claim in modern astronomy belongs to a red supergiant or red hypergiant. Why would the coolest stars also be the widest? The answer connects to how stars fight against their own gravity throughout their entire lives. Every star exists in a constant balancing act. Gravity constantly pulls inward, trying to crush the star down into the smallest, densest object possible. Pressure from nuclear fusion in the core constantly pushes outward, resisting that collapse. For most of a star's life, these two forces roughly balance, holding the star at a stable size for millions or billions of years. Our sun sits in exactly that kind of balance right now. Stable, steady, predictable. But that balance is not permanent. It depends entirely on the type of fuel being burned in the core. Early in a massive star's life, it burns hydrogen, the simplest and most abundant fuel available. That process generates enormous, steady, outward pressure, holding the star at a relatively compact size, despite its huge mass. Eventually, though, the hydrogen runs out, and when it does, the entire internal balance of the star gets thrown into chaos. Without hydrogen fusion in the core, that pressure pushing outward weakens. Gravity, which never stopped pulling inward, suddenly gains the upper hand. The core begins to contract, squeezing tighter under its own weight. Here is the twist that explains everything about this chapter. As the core contracts and heats up further, it becomes hot enough to ignite a new fuel source, helium, fusing it into heavier elements. That new fusion reaction generates a fresh burst of energy. That energy floods outward through the star with tremendous force. The outer layers of the star, no longer as tightly bound to the shrinking core, respond by inflating dramatically. The star swells outward, sometimes to hundreds or even thousands of times its original size, all while the core underneath continues its slow, relentless collapse. This is the exact transformation that turns a massive, compact, blue-white star into a bloated, cool, red supergiant. The core shrinks, the outer layers balloon outward, and because that outward spreading surface now covers such a colossal area, the heat reaching it thins out, dropping the surface temperature even while the star's total energy output stays enormous or even increases. Stephenson 2-18, sitting near or beyond the theoretical limits of how bright a star this cool should be able to burn, may represent one of the most extreme examples of this process ever observed. A star pushed to its outer boundary, stretched about as far as current physics believes possible. This inflation is not a sign of health, it is a sign of a star running out of options. Each new fuel source burns hotter and faster than the last, buying less time than the one before it. A star burning hydrogen might sustain itself for millions of years. The fuel sources that come after burn through in a fraction of that time. Stephenson 2-18 has already made this transition. It has already swollen. It has already cooled, which places it somewhere on a countdown that most stars only pass through once, near the very end of their lives. And to understand exactly where on that countdown this star currently sits, we need to go back to the moment it was first noticed at all, buried in data nobody expected to find anything remarkable in. Let's build this picture, one piece at a time, starting from something you already know, our own solar system. Seen from above, picture the sun sitting at the center, a small, bright dot. Now draw 4 rings close around it. Mercury, Venus, Earth, and Mars, all packed in tight, all crossed easily by sunlight in a matter of minutes. This is the neighborhood most of human history has focused on, our home turf. Now draw a wider ring, this time for the asteroid belt, a scattered field of rock and rubble sitting beyond Mars. Keep going outward, and you reach Jupiter, the largest planet in our solar system, so massive it holds more mass than every other planet combined. Jupiter orbits at roughly 484 million miles from the Sunday. One more ring out, and you reach Saturn, famous for its rings, sitting at an average distance of about 886 million miles from the Sunday. Sunlight itself, moving at the fastest speed physics allows, takes around 80 minutes just to travel that distance. Now take that entire picture, every ring you just drew, from Mercury all the way out to Saturn, and shrink the Sun down to almost nothing by comparison. Replace it with Stephenson 2 to 18. Its outer surface, based on current size estimates, would extend to roughly Saturn's orbital distance. Every ring you pictured a moment ago would sit inside the boiling body of this single star. Try picturing it a different way. Take a basketball court, full length, about 94 feet. If our Sun were shrunk down to the size of a marble sitting at center court, Earth would be a grain of sand sitting about 10 feet away. Jupiter, a slightly larger grain, roughly 50 feet down the court. Saturn would sit almost at the far baseline, nearly 90 feet from that marble. On this same scale, Stephenson 2 to 18 would not be a marble. It would be a beach ball large enough to stretch from one baseline of the court to the other, swallowing the entire length of the game in progress. This is the actual scale we are discussing. Not a big star, not an impressively large star, a star whose outer skin, if placed at the heart of our solar system, would reach out and consume the orbit of a planet we can see through a backyard telescope on a clear night. And remember, this entire structure is held up by gravity fighting against internal pressure, stretched to a size many scientists consider close to the theoretical limit of what a star like this should even be able to reach. Every planet inside that boundary would not slowly heat up and struggle to survive. They would already be gone, absorbed into the star's outer atmosphere the instant the swap occurred. This is the object that currently holds the title of largest known star in the universe. Not a calm, settled giant. A star ballooned out to the ragged edge of what the laws of physics can support. But titles like largest known are not permanent crowns. They get challenged, disputed, and sometimes stripped away entirely as new data rolls in. Stephenson 2 to 18 did not always hold this title, and the story of how it got there and who it took the crown from reveals something important about how science actually works. In 1990, an American astronomer named Charles Bruce Stephenson was combing through data from a deep infrared survey of the northern Milky Way, not searching for a record-breaking star, not chasing headlines, just doing the quiet, patient work of cataloging the sky. Using a telescope called the Burrell-Schmidt, part of the Warner and Swazi Observatory, Stephenson was scanning a region of sky in the constellation Scutum, a faint, easily overlooked patch of stars near the crowded center of our galaxy. Scutum does not contain a single star bright enough to rank among the top 300 brightest stars visible from Earth. It is, by almost every visual measure, unremarkable. Except Stephenson noticed something strange in his infrared data. A tight cluster of stars, glowing with unusual brightness in wavelengths of light invisible to human eyes. He described it, in his own notes, as roughly 10 faint, dust-reddened stars packed into a tiny area of sky, several of them looking like possible red supergiants. He had no way of knowing, at the time, that he had just stumbled onto one of the densest known collections of massive red supergiant stars in the entire Milky Way. Stephenson estimated the cluster's distance at around 98,000 light-years, placing it almost at the outer edge of our galaxy. That estimate, it turns out, was dramatically wrong, not through carelessness, simply because the tools and techniques available in 1990 were nowhere near precise enough to nail down a number that specific, especially for an object buried behind so much obscuring galactic dust. The cluster earned the name Stephenson 2, later also labeled RSGC2, short for Red Supergiant Cluster 2. Inside that cluster sat the star that would eventually become famous. But at first, it was not even counted as a proper member. The brightest star in that region was originally labeled Stephenson 2 to 1. Astronomers noticed it sat slightly apart from the rest of the cluster, shone unusually bright even by the cluster's own extreme standards, and moved through space in a way that did not perfectly match its neighbors. Because of these oddities, it was excluded from the group entirely and reclassified as an unrelated red supergiant, just one that happened to sit in the same direction in the sky. Later research brought the star back into consideration as a possible cluster member, this time renumbering it 18. From that point forward, the star carried the name we use today, Stephenson 2 to 18. That renumbering might sound like a minor bookkeeping detail. It is actually a perfect snapshot of how messy real astronomical discovery tends to be. Nothing about this star's story unfolded in a straight line. It was found by accident, misclassified, tossed out, brought back in, and renamed, all before anyone even settled on how far away it truly sits. And that distance question, more than anything else, is what determined whether Stephenson 2 to 18 would eventually be crowned the largest known star in the universe, or dismissed as an unremarkable, mislabeled giant sitting somewhere else entirely. For years after its discovery, Stephenson 2 to 18 sat in relative obscurity, not because it was unimpressive, because nobody had the tools yet to fully appreciate what they were looking at. The star sits low in the sky, deep within the crowded plane of our galaxy, in a direction thick with gas and dust that scatters and blocks visible light almost completely. Trying to study this region using ordinary optical telescopes is a bit like trying to read a street sign through heavy fog. The information is there, but it is smeared, dimmed, and distorted before it ever reaches your eyes. Infrared observation helps cut through some of that fog, since infrared light passes more easily through dust than visible light does. But infrared astronomy in the early 1990s was still a developing field, limited by the technology of the era. Detailed, high-resolution images of faint, distant clusters buried in dust were simply out of reach. The first genuinely clear image of Stephenson 2 to 18 was not captured until 2007, using data from the 2-micron all-sky survey, taken from an observatory in Chile. That means an object potentially large enough to swallow the orbit of Saturn sat essentially unphotographed in any meaningful detail for 17 years after its initial discovery. Once clearer imaging finally arrived, researchers began taking the star seriously. A team led by astronomer Ben Davies published new distance estimates in 2007 using a technique called kinematic distance measurement. Instead of relying purely on brightness, this method studies how fast an object is moving relative to Earth, using the known rotation pattern of our galaxy to estimate how far away something likely sits. That analysis pulled the cluster's distance dramatically closer than Stephenson's original 1,990 estimate, from nearly 100,000 light-years down to somewhere closer to 19,000. A massive correction, and one that completely reshaped how enormous the stars inside this cluster were understood to be. A separate study in 2010, led by a researcher named Deguchi, arrived at a similar figure, reinforcing the new distance estimate and placing the cluster within a specific structural feature of our galaxy called the Scutum Centaurus arm, one of the great spiral arms that wind outward from the galaxy's core. With a more reliable distance finally in hand, scientists could recalculate the star's true brightness and, from there, estimate its actual physical size for the first time with any real confidence. That calculation produced numbers that stunned the astronomical community. A radius potentially exceeding 2,000 solar radii, a volume nearing 10 billion times that of our Sunday. Suddenly, an obscure red star in an overlooked constellation was being seriously discussed as one of the largest stars ever measured. But being seriously discussed is not the same as being confirmed. Even with better distance estimates, uncertainty still clung to every number attached to this star. And that uncertainty opened the door to a serious scientific debate, one that continues today, about whether Stephenson 2 to 18 truly deserves its record-breaking reputation at all. Here is the number that quietly controls this entire story: 19,000 light-years. That is roughly how far astronomers currently believe Stephenson 2 to 18 sits from Earth. But that number carries a built-in margin of error large enough to completely reshape everything we think we know about this star. Some studies place the distance closer to 18,000 light-years. Others push it out toward 20,000. That gap might sound small in relative terms, but in astronomy, small percentage shifts in distance translate into enormous shifts in calculated size. Here is why that matters so much. Imagine looking at two flashlights in the distance at night, one close and dim, one far away and powerful. From where you stand, they might look identical in brightness. Without knowing the actual distance to each one, you would have no way to tell which flashlight is truly stronger. Stars work the same way. Astronomers measure how bright a star appears from Earth, called apparent brightness. But apparent brightness alone tells you almost nothing about a star's true power. To calculate that, called luminosity, you need an accurate distance. And to calculate a star's physical size, you need both luminosity and surface temperature working together. Every step in that chain multiplies uncertainty rather than cancelling it out. A small error in distance produces a larger error in luminosity. That larger error then produces an even larger error in the final size estimate. Small mistakes compound into big ones. This is precisely why Stephenson 2 to 18 story keeps circling back to distance, again and again. The 1,990 estimate placed the cluster nearly 100,000 light-years away. The 2007 estimate cut that down to around 19,000. Each revision reshaped the star's calculated size dramatically. There is a deeper complication too. Some researchers question whether Stephenson 2 to 18 is even a true member of the Stephenson 2 cluster at all. Remember, this star was originally excluded from the cluster due to its unusual brightness and slightly different motion through space compared to its neighbors. It was only later folded back in as a probable, though not fully certain, member. If Stephenson 2 to 18 actually sits at a different distance than the rest of the cluster, perhaps closer to Earth, appearing bright simply because it is nearer rather than because it is genuinely enormous, then its true size could be significantly smaller than current estimates suggest. This is not idle speculation. It is a real, ongoing point of scientific debate, openly acknowledged in the research surrounding this star. None of this means Stephenson 2 to 18 is secretly small, or that scientists are simply guessing at random. Multiple independent studies using different methods keep landing in a broadly similar range, reinforcing the idea that this really is one of the largest stars known, even if the exact digits remain fuzzy at the edges. But it does mean something important. The crown of largest known star sits on shaky ground, held in place by the best available evidence, yes, but always vulnerable to being knocked loose by the next improved measurement, the next clearer image, the next more precise study. That is exactly what happened to the star that used to wear this crown before Stephenson 2 to 18 ever entered the conversation. Its story is a direct warning about how fragile these record-breaking titles really are. Not every astronomer accepts the 2,150 solar radii figure without hesitation. Some researchers argue the number sits on genuinely shaky ground, and their skepticism deserves a fair hearing, because it reveals exactly how science is supposed to work. The core issue traces back to something we have already touched on: Stephenson 2 to 18 status as a true member of the Stephenson 2 cluster remains unresolved. Some studies treat it as a confirmed member, sitting at the same 19,000 light-year distance as its neighboring stars. Other researchers consider it a foreground object entirely, meaning a star that simply happens to appear in the same direction of the sky, but that may actually sit much closer to Earth, unrelated to the cluster at all. That distinction changes everything. If Stephenson 2 to 18 sits closer to Earth than the cluster itself, its true luminosity would be lower than currently calculated, since some of its apparent brightness would come from proximity rather than raw power. Lower luminosity, worked back through the math, produces a smaller, calculated radius. There is supporting evidence for this doubt too. Researchers have noted that Stephenson 2-18 shows a radial velocity, essentially how fast it appears to move toward or away from us, that differs by about 20 kilometers per second compared to the rest of the cluster. That is a meaningful difference, the kind of detail that raises legitimate red flags about true membership. Some studies suggest an alternate explanation for that mismatch, proposing that Stephenson 2-18 might be surrounded by a thick, expanding shell of gas and dust that it has shed from its own surface. That expanding envelope could distort the velocity reading, making the star appear to be moving differently than it actually is, without necessarily meaning it sits at a different distance at all. This is the messy, honest reality of frontier science. Two competing explanations, both grounded in real data, neither fully settled. Astronomers are not hiding this uncertainty. They are actively publishing it, debating it, and testing it against new observations as better instruments come online. There is a valuable lesson buried inside this uncertainty, one that applies far beyond a single star. Scientific measurement, especially at extreme distances, rarely produces a single, clean, unquestionable number. It produces a range, a best estimate, bounded by known sources of error. Responsible scientists report that range honestly, rather than rounding it off into false confidence. So where does this leave Stephenson 2-18's claim to the title of largest known star? Sitting exactly where honest science usually leaves things. Probably true, strongly supported by multiple lines of evidence, but not beyond all doubt. The star remains the leading candidate. It has not been definitively dethroned, but its crown is genuinely, openly contested. To understand just how quickly a crown like this can change hands, we need to look at the star that held this title before Stephenson 2-18 entered the picture. Its story shows exactly how one improved measurement can shrink a supposed record breaker almost overnight. Before Stephenson 2-18 ever entered the conversation, there was another champion, a red hypergiant named Scuti, and for years, it wore the crown of largest known star without serious challenge. Scuti sits in the same general region of sky as Stephenson 2-18, in the constellation Scutum, though the two are separate stars entirely. German astronomers at the Bonn Observatory first catalogued it back in 1860, though at the time they had no idea what they were actually looking at. It was simply logged as a faint point of light during a broad survey of the sky, given the label BD 12 5055. Decades passed before anyone recognized how strange this star truly was. Later observations revealed it brightened and dimmed on a repeating cycle, about 740 days from peak to peak, marking it as a pulsating variable star, one that physically swells and contracts over time. The real turning point came in 2012, when astronomers used the Very Large Telescope in Chile's Atacama Desert to study Scuti in detail, alongside two other massive stars near the direction of our galaxy's center. The results were stunning. Calculations placed Scuti's radius at roughly 1,700, 8 times that of our Sunday. At that size, Scuti's volume would swallow around 4 billion suns. If placed at the center of our solar system, its outer surface would extend past the orbit of Jupiter, based on the numbers available at the time. News of this discovery spread quickly. Scuti became, for years, the go-to answer whenever anyone asked what the biggest star in the universe was. Documentaries featured it. Countless articles and videos repeated the same staggering comparison. 4 billion suns fitting inside one single star. For nearly a decade, that title held firm. Scuti surpassed the previous record holders of its era, including Betelgeuse, VY Canis Majoris, and NML Cygni, each one a legendary giant in its own right, now pushed into second place. But behind the scenes, a familiar problem was quietly building. The 2012 measurement depended heavily on an assumed distance to the star, roughly 9,500 light-years. And as we have already seen with Stephenson 2-18, Distance estimates in this part of the galaxy tend to be fragile, easily shaken by new data and improved instruments. In the years that followed, a new tool arrived that would change everything. The European Space Agency launched a spacecraft called Gaia, designed specifically to map the precise positions and distances of over 1 billion stars across our galaxy with unprecedented accuracy. When Gaia's data eventually reached UY Scuti, the star's comfortable decade-long reign was about to come to an abrupt and dramatic end. Gaia changed everything, not through some dramatic new discovery, but through something far more powerful in science: better measurement. The Gaia spacecraft uses a technique called parallax to measure distance, essentially observing how a star's apparent position shifts slightly against the background sky as Earth orbits the Sunday. It is the same basic principle as holding a finger up in front of your face and watching it appear to jump left and right as you close one eye, then the other. The size of that shift reveals distance with extraordinary precision, even across thousands of light years. When Gaia's second data release arrived, astronomers used it to recalculate UY Scuti's true distance from Earth. The result placed the star significantly closer than the 9,500 light-years originally assumed, down to somewhere closer to 5,100 light-years. That correction cut the star's calculated size almost in half. Using the new distance, UY Scuti's radius dropped from 1,708 solar radii down to around 755. Still an enormous star, comparable in size to Antares, another well-known red supergiant, but nowhere near large enough to hold onto the title of largest known star in the universe. Later refinements using an even more precise dataset, Gaia's third data release, alongside infrared measurements from a survey called the 2-micron all-sky survey, nudged the estimate slightly upward again to around 909 solar radii. Still, this newer figure sits nowhere close to the star's former glory of over 1,700 solar radii. Picture what that actually means. A star once confidently described as capable of swallowing the orbit of Jupiter got recalculated down to something closer in scale to other well-known red giants, still massive by any human standard, but stripped entirely of its record-breaking reputation almost overnight. This is not a story of scientists making a careless mistake. It is a story of science functioning exactly the way it is supposed to. A new instrument arrived. Better data became available. Researchers applied that data honestly, even though it meant walking back a headline-grabbing claim that had already spread across the internet for nearly a decade. There is an important detail hiding in this story too. Even the newer Gaia measurements come with acknowledged uncertainty, since faint, heavily reddened stars like UY Scuti can introduce noise into these ultra-precise measurements. Astronomers openly note that these newer values, while more reliable than the 2012 estimate, are still not the final word. With UY Scuti's crown removed, the door opened for a new candidate, and Stephenson 2-18, already lurking in the background with its own staggering, uncertain size estimate, stepped forward to fill that gap. This entire sequence, one star rising to fame, then getting quietly recalculated into a smaller, more modest giant, is not a one-time fluke. It reveals a pattern that shows up again and again throughout the history of the largest known star. And that pattern carries a lesson worth remembering. Every time a new record-breaking headline appears, zoom out for a moment, and a clear pattern emerges. The title of largest known star has changed hands again and again over the past several decades, and almost every single handoff followed the exact same script. A star gets measured. Early data, often based on assumed or roughly estimated distances, produces an eye-popping size. That number spreads through headlines, documentaries, and casual conversation, cementing itself as common knowledge. Then, years later, improved instruments arrive, distances get recalculated, and the record-breaking star quietly shrinks back down to something far less extraordinary, replaced by a new challenger riding the same wave of early, uncertain excitement. Betelgeuse held informal bragging rights for decades among casually recognized giant stars. Then VY Canis Majoris entered the picture, with early estimates suggesting a radius that could reach nearly 3,000 times that of our Sun, big enough that its outer layers, some scientists calculated, could stretch beyond the orbit of Saturn if placed at the center of our solar system. Later refinements pulled that estimate down considerably, though it remains an enormous star by any standard. NML Cygni followed a similar arc, briefly holding record-breaking estimates before later measurements scaled things back. UI Scuti then took the spotlight for nearly a decade, only to be dramatically demoted once Gaia's precise parallax measurements arrived. Now Stephenson 2-18 holds the title, itself openly contested, resting on a distance estimate that some researchers still question. This is not a story about scientists being unreliable. It is the opposite. It is a story about science working exactly as intended, constantly checking, correcting, and refining itself as better tools become available. The willingness to overturn a popular, headline-friendly claim, simply because new data demands it, is a sign of a healthy scientific process, not a broken one. There is a useful takeaway hiding here for anyone consuming science content, not just this video. Any claim describing the single biggest, hottest, or most extreme example of something in space should be treated as a current best estimate, not a permanent, unchangeable fact. These titles exist at the very edge of what our instruments can currently measure, which means they sit closest to the edge of potential revision. This does not mean the numbers are worthless, or that Stephenson 2-18's staggering size is make-believe. Multiple independent research teams, using different techniques, keep landing in a broadly similar range for this star, lending real weight to the current estimate. It means holding these record-breaking numbers with open hands rather than a tight grip, ready to update your picture the moment better evidence arrives. With that lesson in mind, we can return to Stephenson 2-18 itself with a clearer, more grounded understanding. Not as an absolute, unquestionable fact, but as our current best window into something genuinely extraordinary happening deep in the constellation Scutum. And that extraordinary thing is not just about size, it is about what size like this actually means for a star's future, because a star swollen out to the edge of physical possibility is not simply large, it is a star running out of road, entering the most volatile, unpredictable stretch of its entire life. To understand what comes next for a star like this, we need to leave the measuring tape behind entirely and step inside the churning, collapsing engine at its core. Every massive star follows a life story with a similar shape, even if the exact details differ from star to star. Birth, a long, stable middle age, then a violent, unstable final act. Stephenson 2-18 sits deep in that final act, in a category of star so extreme it earns its own special name. Astronomers classify it as a red supergiant, and possibly something even more extreme, a red hypergiant. Understanding the difference between these categories and ordinary stars like our Sun unlocks everything about why this star behaves the way it does. Start with mass. Our Sun qualifies as a fairly average, mid-sized star. Stars destined to become red supergiants or hypergiants start their lives far more massive, typically at least 8 times the mass of our Sun, often considerably more. That extra mass changes everything about how a star lives and dies. More massive stars burn through their fuel supply far faster than smaller ones, despite having more of it to burn. Think of it like the difference between a small candle and a massive bonfire. The bonfire holds vastly more fuel, but it also burns through that fuel at a dramatically faster rate, consuming itself in a fraction of the time. Our Sun will shine steadily for roughly 10 billion years total. A star as massive as the ones that become hypergiants might burn through its entire life in just a few million years. A blink of an eye by cosmic standard. For most of that short, intense lifetime, a massive star fuses hydrogen into helium in its core, generating enormous outward pressure that holds the star in a relatively stable, compact size despite its incredible mass. This stage is called the main sequence, and it represents the longest, most stable chapter of a star's existence. Eventually, though, the hydrogen fuel in the core runs out. And this is where the story shifts from stability into something far more dramatic and dangerous. Without fresh hydrogen fusion to generate outward pressure, gravity begins winning its long-running tug-of-war. The core starts to contract, squeezing tighter and heating up as it shrinks. Once the core reaches a high enough temperature, it ignites a new fusion reaction, this time burning helium into heavier elements like carbon and oxygen. This new fusion stage releases a fresh, powerful burst of energy, and that energy pushes outward through the star's outer layers with tremendous force. Those outer layers, no longer tightly bound to a stable, fusion-powered core the way they once were, respond by expanding dramatically, sometimes swelling outward hundreds or even thousands of times beyond the star's original size. This is the exact transformation that turns a massive, compact, blue-white star into the kind of bloated, cool, red giant we have been exploring throughout this story. The star has not gained new material. It has not somehow grown heavier. It has simply redistributed itself, its same mass spread across an enormous, ballooning volume. A red hypergiant represents an even more extreme version of this transformation, among the most massive and luminous stars that exist, sitting at the very outer edge of what stellar physics currently allows. Stephenson 2-18, with its staggering size and luminosity pushing against theoretical limits, fits squarely into this rare and unstable category. But this swollen, inflated state is not where the story ends. It is a transitional, unstable phase, a star caught between one identity and the next. And the driving force behind that instability lies buried deep inside the core, in a slow-motion crisis that has been building for millions of years. Every massive star eventually reaches a point where it cannot simply keep burning the same fuel forever. Stephenson 2-18 has almost certainly already crossed that threshold, and understanding what happens next requires looking at fusion itself, the very process that keeps a star shining, as a countdown clock with a hard stop built into its design. Fusion works by smashing atomic nuclei together with enough force to merge them into heavier elements, releasing energy in the process. Hydrogen fuses into helium, helium fuses into carbon and oxygen, and in the most massive stars, that process keeps climbing the periodic table. Carbon fusing into neon, neon into oxygen, oxygen into silicon, each new stage burning hotter, faster, and through a shorter span of time than the one before it. Here is the detail that makes this countdown so brutal. Each new fusion stage releases less usable energy than the last, even though it requires higher temperatures and more extreme conditions to ignite at all. A star might spend millions of years fusing hydrogen. It might spend only thousands of years fusing helium. By the time a star reaches silicon fusion, that final stage can burn through its fuel supply in a matter of days. This accelerating countdown is the true engine behind a red hypergiant's dramatic, unstable appearance. The bloated outer layers we have spent this entire story exploring are a direct, visible symptom of that internal countdown running its course. The star's structure lurching and readjusting as each new fuel source ignites and burns away faster than the last. There is a hard ending built into this chain, one that cannot be avoided or delayed indefinitely. Fusion releases energy because lighter elements combine into heavier ones, more efficiently packed together, releasing extra energy in the process. That efficiency keeps improving, stage after stage, right up until a star's core starts producing iron. Fusing iron does not release energy, it absorbs energy instead, actually costing the star more than it gains. This marks an absolute dead end. So, a star that reaches an iron core has run out of usable fuel sources entirely. With no further fusion stage available to hold gravity back any longer, we do not yet know exactly how far along this countdown Stephenson 2-18 currently sits. Its swollen size and unusually cool surface strongly suggest it has already moved well past simple hydrogen fusion, likely burning helium or possibly even heavier elements deep within its core. but the exact stage remains hidden from direct observation, buried far beneath the star's visible surface, invisible to any telescope we currently possess. What we do know is this: a star this large, this cool, and this unstable is not sitting in a calm, indefinite holding pattern. It is somewhere on a genuine countdown, one that every sufficiently massive star must eventually complete, whether that ending arrives in 10,000 years or tomorrow. And as that countdown continues, the star does not simply sit still and wait. It sheds itself, piece by piece, into the surrounding darkness of space, in a process that offers some of our clearest visible evidence of just how close to the edge this star has already traveled. Strip away every complicated number and every strange comparison from this story, and one single idea sits underneath everything happening inside Stephenson 2-18. A star is a battle, two forces, locked in constant opposition, and the entire life story of a star is the record of who is currently winning. On one side stands gravity. Every particle of gas inside a star pulls on every other particle, all of that mass constantly trying to collapse inward, trying to crush the star down into the smallest, densest shape possible. Left unopposed, gravity would squeeze a star like Stephenson 2-18 down into a tiny fraction of its current size almost instantly. On the other side stands pressure, generated by the immense heat released through nuclear fusion deep in the core. That heat pushes outward with tremendous force, resisting gravity's constant pull, holding the star's structure open against collapse. For most of a star's life, these two forces settle into a stable standoff. Neither one fully wins. The star holds a roughly consistent size for millions or billions of years, its outward pressure and inward gravity locked in careful balance. Astronomers call this hydrostatic equilibrium, though the concept itself is simple: push and pull, perfectly matched. Our sun sits in exactly this kind of balance right now, and will continue to for billions more years. Stable, predictable, unremarkable, in the best possible sense. Stephenson 2-18 no longer enjoys that kind of balance. Its swollen, oversized structure is direct physical evidence that this tug-of-war has become deeply unstable. The star's core, having burned through its original hydrogen fuel, no longer generates the same steady, reliable pressure it once did. Gravity has gained ground. The core has contracted, and in response, the outer layers have ballooned outward, thin and loosely bound, stretched across a volume nearly 10 billion times that of our Sunday. Think of it like a tightrope walker who has lost their balance pole. For a while, they can still stay upright through frantic, exaggerated movements, arms flailing, body lurching side to side. It looks unstable because it is unstable, even if they have not fallen yet. That is roughly the state Stephenson 2-18 exists in right now. Not collapsed, not destroyed, but visibly, measurably out of balance. Its outer layers stretch to extremes that would have been impossible during its earlier, hydrogen-burning years. This imbalance does not resolve itself quietly. It shows up in dramatic, observable behavior. The star's brightness shifts over time. Its outer layers likely pulse, swelling and contracting in rough cycles. And perhaps most tellingly, the star appears to be losing pieces of itself, shedding material out into space at a rate far beyond anything a stable, balanced star would ever produce. That mass loss is not a side detail. It might be the single most important clue we have about how close Stephenson 2-18 truly sits to the end of its life. And to understand why a star would start shedding itself in the first place, we need to look closer at exactly what is happening deep inside its core, where the real crisis is unfolding. Every star is, at its most basic level, a fight against its own weight. And the fuel that wins that fight, at least temporarily, comes from nuclear fusion happening deep inside the core, hidden far beneath any layer we could ever directly observe. For most of Stephenson 2-18's life, that core almost certainly ran on hydrogen, the simplest, most abundant fuel available in the universe. Hydrogen fusion works by smashing hydrogen nuclei together with enough force to merge them into helium, releasing a burst of energy in the process. Multiply that reaction across countless trillions of collisions happening every second, and you get the steady, reliable outward pressure that holds a star's structure stable for millions of years. But hydrogen, however abundant, is not an infinite resource. Every star carries a finite supply in its core, and massive stars burn through that supply at a staggering pace. A star as large and luminous as Stephenson 2 to 18 likely blazed through its hydrogen reserves in just a handful of million years, a fraction of the time our own sun will spend on the exact same stage of life. Eventually, the hydrogen runs low, then runs out entirely, at least within the star's central core, and when that happens, the entire internal structure of the star is thrown into crisis. Without fresh hydrogen fusion generating outward pressure, gravity, which has been pulling inward the entire time, patiently waiting, finally gains real leverage. The core begins to contract, squeezing down under its own weight, growing hotter and denser as it shrinks. This is not the end of the star's fusion story. It is a transition. As the core contracts and its temperature climbs, it eventually reaches conditions extreme enough to ignite a new fusion reaction, this time burning helium, the leftover product of all that earlier hydrogen fusion, into heavier elements like carbon and oxygen. This new reaction buys the star more time, generating a fresh source of outward pressure, but it comes at a cost. Helium fusion runs hotter, burns faster, and produces less usable energy per reaction than hydrogen fusion did. The star has entered a new stage of life, but it is a stage running on a shorter clock than the one before it. Meanwhile, something dramatic happens to the star's outer layers during this transition. No longer anchored to a stable, steadily fusing core, those outer layers respond to the shifting internal energy by expanding outward, dramatically, sometimes swelling hundreds or thousands of times beyond the star's original size. This is very likely the exact process responsible for transforming whatever compact, blue-white star Stephenson 2 to 18 once was into the swollen, cool, red giant we observe today. Its bloated size is not a separate mystery from its dying core. It is a direct, visible symptom of that core's ongoing struggle. And this struggle does not stop at helium. As each fuel source runs its course, the same pattern repeats, over and over, each time burning a heavier element, each time buying less time than the reaction before it. Stephenson 2 to 18 may already be several stages deep into this accelerating countdown, fusing elements we cannot directly detect from Earth, hidden completely beneath its churning outer atmosphere. Picture climbing a staircase where every single step is shorter than the one before it. That is essentially what happens inside a massive star's core once hydrogen fusion ends. Each new stage of fusion burns through its fuel supply faster than the last, an accelerating countdown baked directly into the physics of atomic nuclei. After helium fusion produces carbon and oxygen, the core, once again running low on usable fuel, contracts further under gravity's relentless pull. That contraction drives the temperature even higher, eventually hot enough to ignite carbon fusion, producing elements like neon, sodium, and magnesium. Carbon fusion burns through its fuel dramatically faster than the helium stage before it, where hydrogen fusion might last millions of years, and helium fusion might last a few 100,000. Carbon fusion in a star, this massive, can complete in a matter of centuries. The staircase keeps climbing. Neon fusion follows, producing oxygen and magnesium, completing in a time span that could be measured in mere years. Then oxygen fusion, producing silicon and sulfur, potentially finishing in months. Finally, silicon fusion ignites, the last meaningful stage available. This process fuses silicon into iron and related elements, and it burns through its fuel with terrifying speed, potentially completing in a matter of days. Stop and compare that to hydrogen fusion. the stage that likely lasted millions of years for a star like Stephenson 2 to 18. By the time a massive star reaches silicon fusion, it is racing through its final fuel reserves in less time than it takes most people to plan a vacation. Why does each stage burn faster than the last? The answer connects to how much usable energy each reaction actually releases. Fusing hydrogen into helium releases an enormous amount of energy relative to the mass involved. Each successive fusion stage, involving heavier and heavier elements, releases progressively less energy per reaction, even though it requires drastically higher temperatures to ignite in the first place. The star has to burn through fuel faster and faster just to generate enough pressure to keep gravity at bay, even briefly. This accelerating process, sometimes called the onion layer structure of a dying massive star, leaves the core looking something like a layered sphere by its final stages. A shrinking iron core at the very center, surrounded by shells of silicon, oxygen, neon, carbon, helium, and finally, a thin remaining layer of hydrogen at the very outer edge, each layer still actively fusing its own specific fuel source, like nested furnaces all burning at once. We do not know exactly which layer Stephenson 2 to 18's core currently sits at. Its swollen size and cool surface temperature strongly suggest it has moved well past simple hydrogen fusion, likely deep into helium burning or beyond. But without a direct window into its core, hidden behind billions of miles of churning outer atmosphere, that exact stage remains genuinely unknown. What we do know is where this staircase inevitably ends. Every single step described in this chapter releases usable energy. The very next element on that staircase does not, and that final energy negative step marks the true point of no return for any star massive enough to reach it. Every fusion reaction we have discussed so far shares one thing in common. Each one releases energy, and that released energy is precisely what holds a star's structure together against the relentless pull of gravity. That pattern holds true, without exception, right up until a star's core begins producing iron. Iron breaks the pattern completely. Fusing iron does not release energy, it consumes energy instead, actually costing the star more than it gains from the reaction. This single fact marks one of the most important thresholds in all of stellar physics. To understand why, picture the process of building something heavier and heavier, brick by brick. Up through silicon fusion, each new element formed is, in a sense, more tightly bound and efficiently packed than the elements that came before it, and that packing efficiency is exactly where the released energy comes from. Iron represents the most tightly bound, most efficiently packed atomic nucleus that exists in nature. Once a star's core reaches iron, there is no more efficiency left to extract. The well has run completely dry. For a massive star, this moment arrives with terrifying speed. Silicon fusion, the stage immediately before iron formation, can complete in a matter of days for a sufficiently massive star. And once that silicon fusion finishes, iron accumulates in the core almost instantly by cosmic standards, within minutes to hours. The moment a star's core becomes dominated by iron, the entire fusion process, the exact process that has held gravity at bay for millions of years, simply stops. There is no next fuel source to ignite, no next stage on the staircase. The outward pressure that has defined the star's entire existence vanishes, essentially all at once. Gravity, which has been waiting patiently through every single stage of this story, finally wins completely and catastrophically. The iron core collapses in on itself, and it does so with almost unimaginable speed, falling inward at a meaningful fraction of the speed of light, completing its collapse in a fraction of a single second. This collapse triggers one of the most violent, energetic events known to exist anywhere in the universe. A core collapse supernova, an explosion so powerful it can, for a brief window of time, outshine an entire galaxy containing hundreds of billions of stars. We do not currently know whether Stephenson 2 to 18's core has reached this stage yet, or whether it still has thousands of years of fusion left to burn through first. Its position on this final staircase remains hidden from us, buried far beneath its visible, churning surface. But here is a genuinely unsettling detail worth sitting with, because Stephenson 2 to 18 sits roughly 19,000 light-years away. The light reaching Earth right now left that star 19,000 years ago. If its core reached this iron threshold at any point during those 19,000 years, the star may have already exploded. We simply would not know yet. The news, traveling at the speed of light, has not finished its journey to reach us. This is not idle speculation designed purely for drama. It is a genuine, sobering feature of how we observe distant space. Every star we study anywhere in the universe is, in a very real sense, a message from the past. And for a star potentially this close to the end of its fusion countdown, that delay carries real weight. Before we sit with that possibility any longer, though, there is something happening on Stephenson 2 to 18's visible surface right now that gives us real, current evidence about how close this star might be to its ending. The star is not sitting still, waiting quietly. It is actively shedding pieces of itself into space. Here lies one of the strangest, most counterintuitive details in this entire story. Stephenson 2 to 18 is not swollen to record-breaking size despite the crisis unfolding in its core. It is swollen precisely because of that crisis. Its enormous size is not a sign of strength. It is a direct, visible symptom of a star running out of stable options. We touched on this earlier, but it deserves a closer, more focused look, because it reshapes how you should think about every biggest star comparison in this entire story. A star's size, at this stage of life, is not a measure of health. It is closer to a fever, a visible sign that something underneath has gone seriously wrong. Recall how this transformation begins. Once a star's core runs out of hydrogen fuel, gravity gains the upper hand, and the core starts contracting under its own weight. That contraction generates intense new heat, hot enough to ignite fresh fusion reactions, first helium, then potentially heavier elements as the process continues. Each time a new fusion stage ignites, it releases a fresh burst of outward-pushing energy. But by this point in a star's life, that energy is no longer generated by a stable, unified core, the way it once was. Instead, it often comes from thin, unstable shells of fusion surrounding a shrinking central core, each shell burning its own specific fuel source, layered together like nested furnaces. These shifting, unstable fusion shells push outward unevenly, sometimes violently, disrupting the star's outer layers rather than gently supporting them the way a stable core once did. The outer layers, no longer anchored to a steady internal structure, respond by expanding dramatically outward, sometimes swelling hundreds or even thousands of times beyond the star's original size. Picture blowing air unevenly into one side of a balloon. Instead of expanding smoothly and evenly, the balloon bulges and distorts, thin and strained in some places, thicker in others. Something similar happens to a star's outer envelope as this unstable internal engine reshapes it. This is why Stephenson 2 to 18's outer layers sit so incredibly far from its core, and why they measure so shockingly thin and diffuse once you get there. The star has not gained new material to fill that expanded volume. It has simply stretched its existing mass across a vastly larger space, leaving its outer atmosphere thin, wispy, and only loosely held in place by gravity. That thin, loosely bound outer structure carries an important consequence. Material sitting at the very edge of a star, this bloated, is far easier for the star to lose entirely, flung outward into space by pulsations, radiation pressure, and the general chaos of an unstable interior. And that is exactly what we observe happening at Stephenson 2 to 18. The star shows clear evidence of dramatic, ongoing mass loss. material actively escaping its outer layers and drifting outward into the surrounding darkness. That mass loss is not a minor side effect. It might be the clearest, most direct evidence available that this star has entered the final, most volatile chapter of its life. Stephenson 2-18 is not a fixed, unchanging object sitting quietly in the darkness. It is actively losing pieces of itself every single year, flinging material outward into the surrounding cluster in a process astronomers call mass loss. This is not unique to Stephenson 2-18. Every star loses some material over time, including our own Sun, which sheds a steady stream of particles called the solar wind. But the scale of mass loss happening at a red hypergiant like Stephenson 2-18 operates on an entirely different level, dramatically more intense and far more consequential to the star's future. Astronomers have detected clear evidence of this process through infrared observations of Stephenson 2-18. The star glows with a strong infrared excess, meaning it emits far more infrared light than its visible surface alone would explain. That excess infrared glow comes from something specific: warm dust and gas surrounding the star, material that the star itself has expelled from its outer layers over time. This shed material does not simply vanish. As gas leaves the star's surface, it cools as it drifts outward into the colder depths of space, and at a certain distance, that cooling gas begins condensing into tiny solid particles, essentially forming dust, similar in principle to how water vapor condenses into clouds here on Earth. That expanding shell of dust and gas surrounds the star, sometimes thick enough to noticeably dim or distort the star's true appearance from our perspective on Earth. This detail actually connects directly back to one of the open scientific debates we explored earlier in this story. Remember that Stephenson 2-18 shows a puzzling difference in velocity compared to its neighboring cluster stars. One proposed explanation involves exactly this expanding envelope of shed material, potentially distorting our velocity readings and complicating efforts to measure the star's true distance and size. Why does mass loss intensify so dramatically at this stage of a star's life? Several forces work together here. The star's outer layers, stretched thin and loosely bound as we explored earlier, sit right at the edge of the star's gravitational grip, making them far easier to strip away. Meanwhile, the star's intense luminosity generates powerful outward radiation pressure, essentially light itself pushing against the thin outer gas with enough force to help push it free entirely. Pulsations, the star's outer layers physically swelling and contracting in repeating cycles, add another push, helping eject material outward during each expansion phase. Together, these forces combine to produce mass loss rates far beyond anything a stable, hydrogen-burning star would ever experience. Some of the most extreme red supergiants and hypergiants studied elsewhere in our galaxy have been observed losing material at rates high enough to strip away a significant fraction of their total mass over just a few thousand years, astonishingly fast by stellar timescales. This matters enormously for what happens next in a star's life story. A star does not necessarily explode carrying all of its original mass. Some of that mass may already be gone, drifted outward into space long before the final core collapse moment arrives. This shedding process actively reshapes the star's future, influencing everything from what kind of supernova it might eventually produce to what remains behind after that explosion finally occurs. Every red supergiant carries what astronomers call a stellar wind, a continuous outward flow of gas escaping the star's outer atmosphere and drifting into surrounding space. For a star like Stephenson 2-18, this is not a gentle breeze. It is closer to a slow, relentless bleeding, carrying away real, measurable amounts of the star's total mass, year after year. To understand just how extreme this becomes, consider our own Sun as a baseline. Our Sun loses mass through its solar wind too, but at an almost negligible rate, roughly 100 trillionth of its total mass every single year. At that pace, the Sun could continue losing mass for longer than the current age of the universe without meaningfully shrinking. Red supergiants operate on a completely different scale. Typical mass loss rates for these stars run in a range roughly 100,000 to 1 million times higher than our Sun's solar wind, and the most extreme examples, stars entering what astronomers sometimes call a superwind phase, can lose mass at rates even higher still. This wind moves relatively slowly compared to winds from hotter, more compact stars, typically drifting outward at somewhere between 20 and 30 miles per second. Slow by stellar standards, but still fast enough to carry material far out into the surrounding region within a relatively short cosmic time frame. Over thousands of years, this steady outward wind builds something remarkable around the star, an expanding shell of gas and dust, growing larger and more structured with each passing century. Around some of the most extreme red supergiants studied in our galaxy, astronomers have identified layered, onion-like shells of previously ejected material, essentially a visible timeline of the star's own mass loss history, each layer representing a different burst of activity from the star's increasingly unstable final centuries. We do not yet have that same detailed, layered picture for Stephenson 2 to 18 specifically. The star sits too far away and too obscured by galactic dust for our current instruments to map its surrounding material in that level of detail. But the infrared excess we discussed earlier tells us clearly that this same basic process is actively happening. Material is leaving. The star is measurably, continuously losing pieces of itself. Here is the deeper significance hiding inside this wind. A star's evolutionary path and its eventual fate does not depend purely on how much mass it started with. It depends heavily on how much mass remains by the time it finally reaches its ending. A star that loses enough of its outer hydrogen envelope through this kind of wind can actually shift its entire future trajectory, potentially evolving away from the red supergiant stage entirely, transforming into a hotter, more compact type of star altogether. That possibility, a star shedding so much material that it fundamentally changes course, is not just theoretical. Some research, specifically focused on Stephenson 2 to 18's cluster environment, has suggested this star may indeed be approaching exactly that kind of transition, potentially on the verge of shedding enough material to begin evolving toward a hotter, bluer stage of its life. That detail changes the entire shape of this story. Stephenson 2 to 18 may not be simply counting down toward a distant supernova in its current form. It might be actively transforming, right now, into something else first. All that gas and dust drifting away from Stephenson 2 to 18 does not simply disappear into empty space. It becomes something new, the raw material for structures that will eventually outlive the star itself. Around many red supergiants and hypergiants studied elsewhere in our galaxy, astronomers have observed exactly this process taking shape. Gas ejected from the star's outer layers drifts outward, cools, and gradually spreads into an expanding cloud surrounding the star, sometimes glowing faintly in infrared light, sometimes forming visible, structured shapes when viewed with powerful telescopes. This expanding cloud of shed stellar material has a name. Astronomers call it circumstellar material, essentially anything surrounding a star that originated from the star itself rather than from its original birth environment. Over thousands of years, as a red supergiant continues shedding mass, this circumstellar material can grow into an increasingly large, complex structure, sometimes stretching across distances that dwarf the star at its center. This detail matters far beyond simple curiosity. That surrounding shell of material plays a direct role in shaping what eventually happens when the star's life finally ends. When a massive star like this eventually explodes as a supernova, the explosion's expanding blast wave does not travel through completely empty space. It slams directly into this pre-existing shell of previously shed material. That collision can produce dramatic effects. In some supernovae, astronomers have observed unusually bright, long-lasting light immediately after the explosion, caused specifically by the blast wave colliding with dense circumstellar material the star had already ejected in its final years or centuries of life. This interaction essentially provides a second source of light on top of the explosion itself, sometimes making the resulting supernova appear brighter or behave differently than a standard explosion happening in truly empty space. For a star potentially as advanced in its dying process as Stephenson 2-18 appears to be, this detail carries real significance. If and when this star eventually explodes, the surrounding material it has already shed through its powerful stellar wind could dramatically shape how that explosion actually appears from Earth, potentially brightening it or altering its characteristic light signature in ways that reveal additional information about the star's final years. There is something almost beautifully cyclical hidden inside this process too. The material a dying star sheds into space does not simply vanish into waste. Much of it eventually becomes the raw ingredients for entirely new generations of stars and planets, gas and dust, drifting through the galaxy until gravity eventually gathers it together again, sparking new stellar birth somewhere else, sometime far in the future. Stephenson 2-18, even in its unstable, dying state, is already contributing to that grand recycling process, scattering material outward that may one day help build something entirely new. But before that new beginning can happen, this star still has one final, dramatic chapter of its own story left to play out. And there are specific, observable warning signs that astronomers watch closely, signs that might reveal exactly how close a star like this sits to its true, explosive ending. Stephenson 2-18 is not a fixed, static ball hanging motionless in space. It breathes. Its outer layers swell outward, then contract back inward, over and over, in a slow, repeating rhythm that astronomers call pulsation. This is not unique to Stephenson 2-18. Red supergiants across our galaxy show this same behavior, and one nearby example gives us an unusually clear, detailed window into exactly what this process looks like. Betelgeuse, a red supergiant close enough to Earth that telescopes can actually resolve features across its surface, pulses on a rough cycle lasting several hundred days, its brightness rising and falling as its outer layers expand and contract in sequence. This pulsation connects directly back to the unstable, shifting fusion happening deep inside the star. Remember the layered, onion-like structure forming inside a star this advanced in its life, multiple fusion shells burning different fuels at different depths. That uneven, shifting energy production does not push outward smoothly and evenly. It surges and eases, again and again, and the star's outer layers respond by swelling and settling in rhythm with those internal surges. There is another piece to this puzzle too, something happening not deep in the core, but much closer to the surface itself. Massive stars like this develop enormous convection cells within their outer layers, essentially giant currents of hot gas rising from deeper, hotter regions toward the surface, cooling, then sinking back down again, similar in basic principle to bubbles rising and falling in a pot of boiling water, except scaled up to sizes that could swallow entire planets. These convection cells are not small. On a star as large as Betelgeuse, a single convective cell can stretch across a meaningful fraction of the star's entire visible surface. As these massive cells rise, brighten, and eventually sink back down, they cause the star's overall brightness to visibly shift and flicker over time, adding yet another layer of instability on top of the star's regular pulsation cycle. In one especially striking, well-documented example, Betelgeuse experienced a dramatic, unexpected dimming event, losing roughly 60% of its normal brightness over just a few months. Researchers eventually traced the cause to a genuinely dramatic event, a massive convective plume rising to the surface, ejecting a huge burst of hot gas outward, which then cooled and formed an obscuring cloud of dust that temporarily blocked a significant portion of the star's light from reaching Earth. That single event revealed something important about stars in this stage of life. They are not gently fading away in a slow, predictable, quiet decline. They are actively, sometimes violently, reshaping themselves, losing real chunks of material in individual bursts, tied directly to the chaotic churning happening inside them. We do not currently have that same detailed, resolved view of Stephenson 2-18's surface. It sits far too distant and too obscured by galactic dust for even our most powerful current telescopes to capture individual surface features the way we can with the much closer Betelgeuse. But based on everything we understand about stars in this category, it is reasonable to expect that Stephenson 2-18 experiences this same basic kind of behavior, pulsing, churning, and periodically shedding bursts of material outward, just on a scale we cannot yet observe in fine detail. This breathing, unstable behavior raises an obvious question. If a star like this is already this dynamic, this volatile, how would we actually know if it was approaching its true, final ending? What signs would even be visible, and which ones remain permanently hidden from us until the very last moment? Here is an uncomfortable truth sitting at the center of this entire story. From the outside, using ordinary light alone, there is no guaranteed, reliable way to tell that a star is about to explode. That claim might sound strange after everything we have explored so far: the swelling, the pulsing, the dramatic mass loss. Surely, you might think, a star behaving this dramatically must be flashing some kind of clear, unmistakable warning sign. The honest scientific answer is more complicated and more humbling than that. Consider Betelgeuse's dramatic dimming event, the one we just explored earlier. For a brief period, headlines around the world speculated that this unusual dimming might signal an imminent supernova, the star's final explosive death, potentially visible even in daylight from Earth. Extensive follow-up research eventually settled the true cause. The dimming resulted from an ordinary, if dramatic, surface mass ejection and dust formation event, not a sign of imminent core collapse. Betelgeuse's outward appearance, even during a genuinely violent episode, did not provide reliable proof of what was actually happening deep in its hidden core. This disconnect exists because of something fundamental about how stars are built. Light generated deep inside a star's core does not travel directly and instantly out to the surface. It gets absorbed and re-emitted over and over, bouncing through the star's dense interior for an extraordinarily long time, sometimes many thousands of years, before finally escaping from the surface as visible light. Whatever chaos might be unfolding right now, deep in a star's hidden core, would not show up in its surface brightness until long after the fact, if it shows up in visible light at all. There is, however, one genuinely reliable early warning signal, and it comes from an entirely different type of particle altogether: neutrinos. Unlike light, neutrinos barely interact with matter at all, passing through a star's dense interior almost instantly, nearly unimpeded, rather than getting trapped and delayed for thousands of years. During a star's final, frantic fusion stages, particularly while burning silicon in its innermost core, the star produces a measurable, detectable surge in neutrino output, escaping the star almost immediately as that final stage unfolds. Scientists have built dedicated networks of neutrino detectors specifically to catch this exact signal, an international collaboration called the Supernova Early Warning System. These detectors, built using massive tanks of water or other specialized materials buried deep underground to shield them from unrelated background interference, stand ready to catch that telltale surge of neutrinos, potentially providing advance warning hours, or in rare cases, even days, before a star's core visibly collapses and the resulting explosion becomes observable through ordinary light. This detection method currently only works for genuinely nearby stars, generally within our own close cosmic neighborhood, since the neutrino signal involved is faint and difficult to detect reliably across truly vast distances. Stephenson, 2 to 18, sitting 19,000 light-years away, currently sits far beyond the reliable detection range of these existing neutrino networks. This leaves us with a genuinely honest, unresolved mystery at the heart of this entire story. We cannot currently know, with any real confidence, exactly how close Stephenson 2 to 18 sits to its true ending. Its swollen size, its cool surface, its dramatic mass loss all strongly suggest a star deep into its final, unstable chapter. But whether that ending arrives in 10,000 years, or has, in some sense, already happened during the 19,000 years its light has spent traveling toward us, remains genuinely unknown. That uncertainty does not make the story less compelling. It makes it more honest, and it sets up the final, most dramatic question left to explore. If and when Stephenson 2 to 18 truly does reach its ending, what would that explosion actually look like? And what would be left behind once the dust finally settles? Picture the single most violent event most people will ever witness in their lifetime, and then multiply that intensity by numbers too large to comfortably picture. That gives you some sense of what a supernova from a star like Stephenson 2 to 18 might actually look like if and when it finally happens. A core collapse supernova, the specific type triggered by a massive star's iron core suddenly giving way to gravity, unleashes an almost incomprehensible amount of energy in an extraordinarily short window of time. For a brief period, sometimes lasting just days or weeks, a single exploding star can outshine its entire host galaxy, a galaxy containing hundreds of billions of individual stars, all combined. The exact character of Stephenson 2 to 18's eventual explosion would depend heavily on details we currently cannot fully confirm, particularly how much of its outer hydrogen envelope remains intact by the time its core finally collapses. Remember the dramatic mass loss we explored earlier in this story. A star that has already shed a large portion of its outer hydrogen layers through years of intense stellar wind produces a noticeably different kind of explosion than one that still holds most of its original envelope intact. If Stephenson 2 to 18 retains a substantial hydrogen envelope by the time it explodes, astronomers would classify the resulting event as a Type 2 supernova, one of the most common categories observed among massive, dying stars. These explosions typically show a distinctive light signature, a sharp initial burst of brightness, followed by an extended plateau phase where the brightness holds relatively steady for an extended period, powered by the explosion's shockwave interacting with that remaining hydrogen envelope. There is another dramatic possibility worth considering too, one directly connected to everything we explored about this star's ongoing mass loss. If Stephenson 2 to 18's stellar wind has already built up a substantial shell of gas and dust surrounding the star, its final explosion could slam directly into that pre-existing material. That collision can produce an unusually bright, longer-lasting burst of light, sometimes classified as a distinct supernova subtype entirely, one where the explosion's brightness gets amplified by crashing into material the star itself had already ejected in its final years or centuries of life. Beyond simple brightness, a supernova from a star this massive would release far more than light. It would blast heavy elements outward into surrounding space at tremendous speed, elements forged deep inside the star through billions of individual fusion reactions across its lifetime. Every element heavier than iron found anywhere in the universe, including many elements essential to life as we understand it, traces its origin back to explosive events exactly like this one. If Stephenson 2 to 18 exploded today, and if that explosion happened to be visible from Earth, it would likely appear as an extraordinarily bright new point of light in the constellation Scutum, potentially rivaling some of the brightest planets in our night sky for a period of weeks or months, before gradually fading as the explosion's initial burst of light subsides. But remember the delay built into this entire story. Light from Stephenson 2 to 18 takes 19,000 years to reach Earth. Whatever we observe happening at this star right now already happened 19,000 years in the past. which raises a question worth sitting with directly, rather than glossing over. Could this star have already exploded sometime during those 19,000 years, without us knowing yet at all? Here is a genuinely strange feature of observing anything at extreme cosmic distances. You are never looking at the present. You are looking at the past, frozen in transit, carried toward you at the fastest speed the universe allows. Stephenson 2 to 18 sits roughly 19,000 light-years from Earth. That distance means the light currently reaching our telescopes left the star's surface 19,000 years ago, long before recorded human history began, back when early humans were still living through the tail end of the last ice age. Everything we have discussed throughout this entire story, the star's staggering size, its cool red glow, its dramatic mass loss, its apparent instability, describes conditions as they existed 19,000 years in the past. We have no direct way of knowing what has happened at that location since that light departed. This raises a genuinely legitimate possibility, one grounded in real physics rather than idle speculation. If Stephenson 2 to 18's core reached its final, catastrophic collapse at any point during those 19,000 intervening years, the star may have already exploded. The light from that eventual explosion, traveling at the same fixed speed as everything else, simply has not finished its own 19,000-year journey to reach us yet. In a very real sense, we are watching a 19,000-year-old recording, with no way to fast forward to see what happens next. Only the ability to wait patiently for future light to eventually arrive and reveal it. Does this mean Stephenson 2 to 18 has already exploded? Not necessarily. Stars at this stage of life, swollen, unstable, and actively shedding mass, can persist in this dramatic condition for a genuinely long time by human standards, potentially tens of thousands of years, before finally reaching that irreversible iron core collapse. 19,000 years, while significant, may represent only a small fraction of the total time this star spends in its current unstable phase. But it also means we simply cannot rule out the alternative. Somewhere in that 19,000-year gap between what we currently observe and what is actually happening right now at that location, this star's fate may have already been decided, one way or another. This uncomfortable uncertainty is not a flaw specific to this one star. It applies to literally everything we observe at meaningful cosmic distances. Every galaxy, every star, every distant object studied by astronomers represents a snapshot from the past, sometimes a very recent past, sometimes a past stretching back billions of years. Understanding the true current state of the universe requires constantly remembering that what we see and what currently exists are not necessarily the same thing. For Stephenson 2 to 18 specifically, this means the title we have spent this entire story exploring, largest known star in the universe, comes with a genuinely strange asterisk attached. We are potentially describing a star that no longer exists in its current form, crowning an object that may have already transformed into something else entirely, sometime during the 19,000 years its own light has spent traveling toward us. Whether that transformation has already happened or still lies far in the future, the physics governing what comes next remains the same. And that physics reveals something fascinating about how a star's own properties help determine exactly what gets left behind once the explosion, whenever it truly occurs, finally runs its course. Picture the moment immediately following a supernova explosion, the actual physical aftermath, once the initial, blinding burst of light finally begins to fade. The space surrounding what used to be Stephenson 2 to 18 would look nothing like it did before, transformed almost instantly into something entirely new. The explosion itself launches material outward at tremendous speed. In many observed supernovae, ejected gas travels at speeds reaching several percent of the speed of light itself. That expanding wave of debris slams into the surrounding environment, including, as we explored earlier, any material the star had already shed through its own stellar wind during its final unstable centuries or millennia of life. That collision between fresh explosive debris and older, previously shed material generates its own dramatic light and structure, sometimes producing an expanding, glowing shell that remains visible to telescopes for centuries or even thousands of years after the initial explosion. Astronomers call these structures supernova remnants, and several stunning, well-studied examples exist scattered across our own galaxy, some clearly visible even through relatively modest telescopes here on Earth. Inside that expanding, glowing shell of debris sits newly created material, heavy elements forged during the star's final fusion stages, and additional heavier elements created in the explosion itself, flung outward into the surrounding galaxy. This material does not remain isolated forever. Over time, spanning many thousands of years, this expanding cloud of enriched gas gradually mixes into the broader interstellar medium. The vast reservoir of gas and dust spread throughout our galaxy that eventually seeds the formation of entirely new stars and planetary systems. There is something worth appreciating in this process. Beyond simple destruction, every heavy element that makes complex chemistry, and ultimately life itself, possible anywhere in the universe, traces its ultimate origin back to explosive events exactly like this one. Elements like calcium, iron, and oxygen, essential to biology as we understand it, were forged inside the cores of massive, dying stars, then scattered outward through explosions like the one Stephenson 2-18 will eventually produce. Meanwhile, at the very center of that expanding debris cloud, something else remains behind, a small, incredibly dense object left over from the star's collapsed core, the true physical remnant of everything that previously made up this colossal star. What exactly that remnant becomes, and how dense and extreme it truly is, depends on one final, crucial factor that we have not yet fully explored. A factor tied directly back to exactly how much mass Stephenson 2-18 retains by the time its core finally, irreversibly collapses. Once a massive star's core finally collapses, the wreckage left behind takes one of two dramatically different forms. Either a neutron star, one of the densest objects known to exist, or something even more extreme, a black hole, an object so dense that not even light can escape its pull. What decides which of these two outcomes a star like Stephenson 2-18 would produce comes down almost entirely to one factor: mass. Specifically, how much mass remains packed into the star's collapsing core at the exact moment its fusion finally runs out. Picture squeezing a sponge. Squeeze gently, and it compresses only a little before pushing back, resisting further compression. Squeeze with enough force, though, and eventually you overwhelm that resistance completely. A collapsing stellar core behaves in a strikingly similar way, except the force involved is gravity itself, and the resistance comes from the fundamental behavior of matter under extreme pressure. If the collapsing core contains roughly between 1.5 and 2.5 times the mass of our Sun, something called neutron degeneracy pressure kicks in and successfully halts the collapse. This pressure arises from a strange quantum mechanical rule stating that certain particles, in this case neutrons, cannot be squeezed into the exact same space and state simultaneously. That resistance, though invisible and strange, is strong enough to stop gravity's collapse cold, leaving behind an incredibly dense, city-sized sphere called a neutron star, so dense that a single teaspoon of its material would weigh roughly as much as a mountain here on Earth. But if the collapsing core exceeds that threshold, carrying more mass than neutron degeneracy pressure can successfully resist, the collapse simply does not stop. Gravity wins completely and permanently. The core keeps collapsing inward, past the point where any known force in the universe can halt it, ultimately forming a black hole, an object so dense that its own gravity prevents even light itself from escaping. Where might Stephenson 2-18 fall along this threshold? This is genuinely difficult to answer with confidence, largely because the star's true total mass remains one of its most uncertain properties, estimates ranging anywhere from roughly 10 to 40 times the mass of our Sunday. Layer on top of that the dramatic mass loss we explored earlier in this story. Material actively escaping the star through its powerful stellar wind, potentially stripping away a meaningful fraction of its original mass before its core ever collapses at all, and the final answer becomes genuinely difficult to predict with any real precision. What we can say is this: stars massive enough to become extreme red hypergiants, like Stephenson 2 to 18, generally sit within a mass range capable of producing either outcome, depending heavily on exactly how much material the star retains by the time collapse finally occurs. Some research suggests progenitor stars retaining a substantial envelope at collapse tend to favor black hole formation, particularly once original masses climb into the higher end of the possible range for this star. There is a strange, almost poetic twist buried in this uncertainty. The very same dramatic mass loss that has shaped this entire story, the shedding, the pulsing, the swelling outer layers we have spent so much time exploring, may ultimately be the deciding factor in whether Stephenson 2 to 18 ends its life as a dense neutron star or vanishes entirely behind the event horizon of a newly formed black hole. Either outcome represents an extraordinary transformation. A star currently wide enough to swallow the orbit of Saturn, eventually compressed down into an object potentially no larger than a city, or smaller still, disappearing completely into the strange, warped fabric of a black hole's gravity. Stephenson 2 to 18's story is not simply about one unusually large star sitting far away in the constellation Scutum. It is a working example, a genuine case study of exactly how astronomers hunt for the biggest, most extreme objects hidden throughout our galaxy and beyond. Every technique explored throughout this story, measuring distance through kinematic methods and precise parallax, calculating luminosity from brightness and distance combined, deriving physical size from luminosity and temperature together, represents a toolkit astronomers apply again and again across countless other stars scattered throughout the Milky Way and neighboring galaxies. The mistakes and corrections woven throughout this story matter just as much as the successes. UY Scuti's dramatic demotion from record holder to a more modest, though still enormous, red supergiant serves as a permanent, working lesson for the entire field. Distance estimates in dusty, crowded regions of our galaxy carry genuine uncertainty, and that uncertainty directly shapes every downstream calculation built on top of it. Astronomers studying other candidate giant stars now apply that hard-earned lesson directly, treating early size estimates with appropriate caution until multiple independent methods converge on a consistent answer. Tools like the Gaia spacecraft, responsible for dethroning UY Scuti through dramatically improved distance measurements, continue mapping the precise positions and distances of over 1 billion stars across our galaxy. Each new data release from that mission has the potential to reshape our understanding of countless other stars, not just the handful discussed prominently in this story. Somewhere in that enormous dataset, currently unrecognized giants may already be hiding, waiting for the right analysis to reveal their true, staggering scale. There is a bigger, more sweeping question hiding underneath all of this too. Stephenson 2 to 18 sits within our own galaxy, the Milky Way, one of hundreds of billions of galaxies scattered throughout the observable universe. Every single one of those other galaxies almost certainly contains its own population of massive, unstable, red hypergiant stars, objects potentially rivaling or even exceeding Stephenson 2, 18 inches true physical size. We simply have not found them yet, and in many cases, given the tremendous distances involved, we may never develop the tools capable of measuring them with any real precision. Stephenson 2 to 18 holds its current title, not necessarily because it is truly the single largest star existing anywhere in the universe, but because it happens to be the largest star we have successfully identified and measured so far, with our current generation of telescopes and techniques. Sitting relatively nearby within our own galaxy, this distinction matters enormously. The universe almost certainly contains stars larger than anything discussed throughout this entire story, hidden in galaxies too distant, too faint, or too obscured for current instruments to resolve in the necessary detail. Stephenson 2-18's crown, much like every crown before it, exists as a snapshot of our current knowledge, not a final, permanent statement about the true limits of what exists across the wider universe. Future telescopes, more sensitive, more precise, capable of piercing through galactic dust with greater clarity than anything currently available, will almost certainly continue this pattern, discovering new candidates, refining old measurements, and potentially dethroning Stephenson 2-18 itself, the exact same way it once dethroned UY Scuti before it. After everything explored throughout this story, from staggering size comparisons to the deep physics driving a star toward its final collapse, one honest conclusion remains standing above all the rest. Stephenson 2-18 remains, in many meaningful ways, a genuine mystery. We do not know, with full certainty, its true distance from Earth, a number that directly shapes every other measurement built on top of it. We do not know, with full confidence, whether it truly belongs to the Stephenson 2 cluster it was named after, or whether it sits somewhere else entirely, coincidentally aligned in the same direction of the sky. We do not know its precise mass, a figure that could ultimately decide whether this star ends its life as a dense neutron star, or vanishes completely into a newly formed black hole. We do not know exactly which stage of fusion currently burns within its hidden core, buried far beneath billions of miles of churning, unstable outer atmosphere. We do not know how close this star genuinely sits to its final, explosive ending, whether that moment lies thousands of years in our future, or whether, due to the 19,000 years its light has already spent traveling toward us, that ending may have already happened, the news simply still in transit. This list of unknowns might initially sound discouraging, an admission of how little we truly understand about an object we have spent this entire story exploring in such vivid detail. But consider it from a different angle instead. Every single unknown listed here represents an active, ongoing frontier of genuine scientific investigation. Questions actively being pursued right now, using tools and techniques constantly improving with each passing year. Stephenson 2-18 currently holds the title of largest known star in the universe. Not the largest star that exists, a distinction worth remembering clearly. The largest star we have successfully found, measured, and confirmed so far, using the best instruments and techniques currently available to humanity. That distinction captures something genuinely important about science as a whole, extending far beyond this single star. Our current understanding represents our best available answer, built carefully from the strongest evidence currently in hand, always ready to be refined, corrected, or completely overturned the moment better evidence finally arrives. Somewhere out there, hidden in the vast, largely unmapped depths of our own galaxy, or scattered among the hundreds of billions of other galaxies filling the observable universe, stars potentially larger, stranger, and more extreme than Stephenson 2-18 almost certainly exist right now, patiently waiting to be discovered by the next generation of telescopes and researchers. For now, though, the crown belongs to this one star, a colossal, swollen red giant, hanging in the darkness of Scutum, its true fate hidden behind a curtain of distance and time we cannot yet fully pierce. 19,000 years of light, still traveling toward us, still carrying the answer to whether this star remains exactly as we see it tonight, or whether its true ending has already come and gone, quietly, long before we ever knew to look.